In this video, we're going to build a simple NFT. Now, it will loosely follow the ERC721 specification, but we won't follow it exactly just for the sake of simplicity. You shouldn't use this code in production. Everybody uses the OpenZeppelin library, which I'll get to later, and there's a good reason for that. However, if we dive into OpenZeppelin right now, there's going to be a lot of code to look at, and I think it will make it harder to understand what's going on. So we'll build the core functionality by hand here, and then move on to OpenZeppelin once you know enough, and just use that for the rest of the course. Okay, let's go. The most important thing in an NFT is the associative array between users and the tokens that they owned. So you're always going to see something like this, a mapping from uint256 to address, and this will be private, and we'll call it owners. Now, why are we going from token ID to address rather than the other way around? The reason for that is because you can know in advance which token IDs you're going to produce, but you can't know in advance which addresses are going to own it. And you cannot iterate over mappings inside of Solidity. So let's say you know that your token IDs are going to be 0, 1, 2, etc., up until 100, then you can just loop through all of the keys here and figure out who the owners are. But you can't do it the other way, not without storing an additional list of addresses, and that's going to force the contract to store more things and be more gas heavy. So let's do that. And the next thing that we're going to care about is, obviously, if we query the token ID, we want to know who owns it. Well, let's fulfill this specification bit by bit. So an ERC721 token needs to fulfill all of these functions, which we're obviously going to study each of these in detail. But the first thing that we care about is the owner of. We care about who owns the tokens, kind of obviously, right? And that's the function owner of, and it's saying it needs to have this signature over here. It needs to take a token ID and return the owner, which is the address. So we will do that. We will return owner's token ID. Now, this leads to an interesting question. What if you specify a token ID that is not part of the collection? Like, let's say token 101 is not part of the collection. This thing is going to return the 0 address, because that's what mappings do if you ask for a key that's not inside of, that hasn't been specified before. It defaults to the 0 value. According to the specification, it says NFTs assigned to the 0 address are invalid, and queries about them do throw. So it should throw an exception. So what are we going to do about that specification that it should throw? Well, we can just have a require statement, right? So the require statement will cause the transaction to revert. If somebody asks for a token ID that hasn't been minted yet, then we shouldn't say the 0 address owns it. It should cause the transaction to revert. So let's say require owners token ID does not equal the 0 address. No such token. Okay, so we fulfilled the owner of. Obviously, this is going to return an exception each time, because there's no mechanism inside of this contract for things to be minted. Okay, let's add that. Now, the interesting thing here is that the ERC721 specification doesn't really say how you should mint things. It kind of leaves that up to you. So if you actually read that part of the specification here, it says creation of NFTs minting and destruction of NFTs burning is not included in the specification. Your contract may implement these by other means. See the event documentation for your responsibility when creating or destroying NFTs. Don't worry, we will get to that later, but we need to create a mechanism for minting NFTs. So let's do that. Function mint uint256 token ID external. So just to keep things simple for now, we're going to say anybody can mint an NFT for themselves using whatever token ID they like. This is obviously an extremely bad design. We should have some restrictions around what token ID you can put in there, and restrictions around who can mint, and we probably want to charge them money to do that. But just for the sake of simplicity, I'm going to create a very simple mint function that gets the job done and puts tokens into existence. So what we're going to do is say owners token ID. So this is going to create a new entry inside of this mapping and set it to message.sender. Okay. Now we do have a problem here, because we probably want to revert this if someone already minted a token, because we don't want to just overwrite token ownership. Let's say I come in and I mint token 10 and I set it to my address, and then you come in and then set your address to mint token 10. Well, you've just stolen the token from me. So let's require that the owners of the token ID is equal to the 0 address. So that way you can only mint token IDs that have not been taken yet. And just to make this more interesting, because you could really mint a wide range of token IDs, just most NFTs have a limited supply. at least the way that they're currently used. So just for the sake of it, let's also say that you can't mint a token ID bigger than 100. So we're going to require that the token ID is less than 100. So everything is going to go from 0 to 99. Token ID to large. Okay, so this function can only be called for numbers 0 through 99. And that's going to effectively limit our supply. Now, this is not the way people normally do it, but just for the sake of simplicity, I'm going to implement it this way. Okay, so we have an ability to bring tokens into existence and a way to ask who owns them. Let's test this out. So I'm going to compile, and I'm going to deploy this. Now, let's try it out. So I'm going to mint token ID 7 for myself. I mint, and who is the owner of token 7? Well, it's going to be 0x5b3, which is, of course, the default first address inside of the Remix environment. Okay, that's pretty simple. Now, this, of course, is not interesting because once it's minted to me, I just own it forever. So we need to implement an ability to transfer it. What you see here, there's actually a safe transfer from and another safe transfer from, and a transfer from. What is the difference between all of these? Well, if you look at their different signatures, let's compare these two because they have the same function name. The difference between them is bytes. So if you wanted to initiate a transfer and send some additional information along with the transfer, like let's say, thanks for doing business, then you could put that message inside of here. But if you didn't care about that, you just say, I want to transfer from this address to this address, and this is the token ID that I want to move. That's what you would normally do. So what's the difference between safe transfer from and transfer from? Because clearly they're both taking the same exact parameters here. Well, safe transfer from is going to first check if the recipient is a smart contract. Because if you transfer an NFT to a smart contract and that smart contract does not have the ability to transfer the NFT again, then the NFT will be stuck there and be effectively useless. So there are two mechanisms for this. The safe transfer from is more complicated because it checks if the recipient is a smart contract. So for now, we're going to skip that and we're going to implement transfer from. So let's do that. Now, transfer from to and token ID. This is actually pretty simple. We're going to take our mapping of owners, and remember the key is the token ID. So this token ID is going to be set to the recipient, which is 2. Now, hopefully you're noticing a very obvious problem with this. One is, first of all, we don't know if this actually came from this address. This could have been owned by somebody else. And also, we don't want to just call anyone to be able to call this function because you could just steal NFTs from people. I'll just call this and, hey, you have token 7. I'm just going to take it from you. And the other thing we need to check for is we need to check if the token ID actually exists. Okay, so first of all, let's check if the token ID exists. So we're going to require that owners of token ID is not equal to the 0 address. Then we're going to require that the address from is actually the owner of the token. And the other thing that we'll want to do, remember, we don't want just anybody to call this function. So there's actually a little bit more complication to this because you might be thinking, well, the only person who's going to be calling transfer from is going to be the person who owns the token because only the owner should be able to transfer their token, right? Well, yes, that's true, but there's actually an additional specification inside of ERC721 where you can allow other people to transfer tokens on their behalf if you give them the privilege to. We'll get to that in a bit, but for now, let's just keep it simple and say from has to be message.sender. So require message.sender is equal to from. So this means only people who own the token are able to transfer it, okay? This is not actually fulfilling the specification. This is wrong, but I'm not trying to be super close to this thing. I'm just trying to give you an idea of what's going on. So let's recompile this thing and get rid of the old one here and deploy it. Okay, let's mint token 4 for ourselves. We see that we are the owner of, and now let's commence the transfer. So from myself, and now let's transfer the NFT to another address. Let's say this guy, copy this address, and 2, and I'm going to transfer token 4. Now, because if I initiate the transaction right now, I'm not initiating it from the account, from the actual NFT owner. So if I hit transact here, it's just going to fail. As you can see here, boom, can't do that. You are required to be the owner. Okay, so our security worked here. Now let's actually switch to be the owner and transact. Okay, that succeeded. Now if we ask for the owner of 4 again, now it's going to change to AB8. Okay, what I want to do now is make sure that what we're doing is actually on track with how NFTs are actually used in the real world right now. I don't want to just keep, okay, we're following a spec, we're building an NFT. We want to build NFTs that people are actually using. So let's see the relationship between the functions that we're creating here and how NFTs are used on, say, OpenSea. So let's go to OpenSea.io and let us look at the Cool Cats collection. Cool cats. Okay, now let's see who owns this cat. And when we look at details, we're going to see the contract address and the token ID. Okay, now I want you to remember 8696, because remember how we were minting like token 4 to ourselves last time? Well, this is token 8696. Let's see how the relationship between what's inside of this smart contract and what we've been doing. So I'm going to open up this thing, and it's going to take me to Etherscan, and I am going to hit contract, read the contract, and look for owner of. There it is. So if I put in 8696 and query it, it's going to say the owner of this is FCFC32 something something C5E. Well, is that the actual owner of this? Well, if we go look at what OpenSea is saying, then it's going to say it's owned by NFT Boho. And let's see this guy's Ethereum address, or girl, I don't actually know. So if I click down, it says 0FCFCC5E, which is exactly what we have here. Okay, that's pretty cool. If you wanted to transfer this, well, you cannot because you don't own this NFT, I presume. Here we can see this contract fulfilling the safe transfer from and the transfer from. If this was initiated, we see the same arguments that we saw earlier, the from it and the to and the token ID. All right, cool. Now, of course, a very natural question is, well, where's the JPEG? Well, that is what we are going to look at. We are going to implement the TokenURI function. And when we put in 8696 in here, then what it's going to do is give us back a resource ID. And it says coolcatsnft.com/cat/8696. And we put that into our browser. And we actually get a JSON file back. Now, this might seem a little bit counterintuitive because we thought, okay, wait a minute, aren't these supposed to be JPEGs? Well, traditionally, how NFTs are configured nowadays is that resource URL points you to a JSON file that allows you to put extra metadata about the NFT. So it says it's a blue cat and it has a hat and the hat is visor blue. That is where OpenSea, if I go back here, is getting this information. Blue cat skin, hat visor blue, and so forth. There were other traits that I didn't read off, but they're all listed there. Now let us look at the actual image. So if you look at the image field inside of this JSON file, then we can copy this, input it over here, and there is the actual cat stored on IPFS. Don't worry if you don't know what IPFS is right now. That is something that we will discuss later. Now what we want to do is replicate the mechanism that this CoolCats contract is doing so that we can store JPEGs. Okay, what we will need is a URL. So originally, CoolCats was storing them inside of something like this. So they had something like string, let's call it base URL is equal to api.coolcatsnft.com/cat/this. Okay, but we don't want to hard code this. We want this to be a number that we're going to put in there, which is going to be a number from 0 to 99. And we also are not doing the CoolCats NFT. We're using our own. So I'm just going to say example.com/images. There's, of course, nothing there, but you get the point. Now, one thing you might be noting is, hey, wait a minute. Couldn't we just point these JPEGs to the CoolCat and then copy it? Well, no, because that's not what makes NFTs unique, as we talked about earlier. It's the combination of the smart contract address and the token ID that makes NFTs unique, not the resources that they point to off-chain. So we have our base URL. Next thing we're going to want to be doing is concatenating. Well, you can't concatenate in Solidity, but we want to be building a string that's going to contain the integer in here that corresponds to our token. Now, but what was the interface for getting back the URL? Well, remember when we looked back here, we were looking at TokenURI was the function that told us where the actual image was stored, or rather where the JSON was, which told us where the image was stored. And this is not a coincidence. This is part of the ERC721 specification. So I'm going to go back there. If we look at TokenURI, then this is part of the interface that gives us a distinct uniform resource identifier for a given asset, and it throws token ID as not valid. So this is the resource identifier, which in this case is an HTTP URL, or it could be an IPFS URL, but don't worry about that. We'll get to that later. Okay, let's paste this in here. What we want to do is return, or at least at the end of when everything is completed, if someone asks for, let's say, token 5, then we want to return this. So how can we go about doing this? Well, we don't want to hard code it. What we will want to do is, first of all, fulfill the specification and check, hey, is this actually existing? Because we don't want to return a URL if someone says 101. Remember, 101 is not a valid token ID. So we don't want to say example.com/images/101 because that would be wrong. So what we were going to do is require that the owners of token ID is not equal to the 0 address. Does not exist. Now let's return the actual string here. So I'm going to show you how to do this wrong, and then I'm going to show you how to fix it. Otherwise, I'm going to just be giving you too much new code, and you're going to be wondering why I'm doing it. So I'm going to return a string by doing this. Return string. So what I'm going to do is going to be cast to a string, and I'm going to say abi.encode packed base URL, and I'm going to put the token ID in there. Okay. Well, first of all, something breaks. It says data location must be memory or call data for return type. So it's saying this needs to have a memory keyword in there because strings are stored in memory. Now, why on earth was the solidity code that they gave us inside of the EIP specification wrong? Well, it wasn't. This is for an interface specification. It's not for the actual contract. But since we are not building an interface here, we're building the actual contract, we need to say where the string is stored, and strings are either memory or call data. Call data only applies if it's inside of the function arguments, and this is not a function argument, it's a return type. Okay, so we have this. Now you're going to actually see some funny results here. So if I deploy this contract, and first of all, if I try to ask, hey, what's the TokenURI for 5? It's going to give me an error. It says revert here. So that's what we expected. Let's mint token 5 so that we don't have that problem. And then when we get TokenURI back, it's empty. It's only giving us the base URL. What happened? Well, this is not a string. This is an integer, and we are effectively trying to mix these two types together, which is just not going to work. So if we wanted to convert this thing to a string, well, ideally we would do something like toString over here, but unfortunately, this is not valid solidity. We need to import a library to do this. And luckily, OpenZeppelin provides us a nice utility for that. We're going to import OpenZeppelin to get that toString functionality. So if I look at OpenZeppelin contracts on GitHub, then we will be able to recover the path that we need for that. So if I look inside of contracts, and I'm going to look inside of utils, and I'm going to look at strings, and here in this library, we have a toString utility, which is going to take the uint256 and return the string. This is actually some pretty complicated code here, so luckily we don't have to do that ourselves. Well, let's go back to Remix. We're going to need to remember this. We're going to import at OpenZeppelin /contract/strings.sol, and then, whoops, what's going on here? Sorry. Let me just comment out this broken code for now and return an empty string so that the compiler stops yelling at us. Now, what just happened when I did this? Well, if I look inside of the file explorer and then go to npm/OpenZeppelin, then here we have strings.sol. That thing from GitHub just got dropped in here. That's what this at thing is doing. Like this, we're basically just taking a shortcut and doing an npm install for OpenZeppelin. And then we are following the same path inside of the GitHub in order to get the utility back. So to make this .toString valid, what we need to do is associate this library with the uint256. So if we say using strings for uint256, what that is going to do is associate this library with uint256. So if we call .toString on a uint256, then that's effectively going to put that uint256 inside of this function argument and just give us the string back. So that's, I know this is throwing a bit more information at you, but you're going to see this pattern all the time, so we might as well learn it now. So let's go back here and uncomment this, get rid of this, and now this should work as expected. If we wanted to say .jpeg at the end, then we could just say .jpeg, and now all of these things are going to fall together quite nicely. So I compiled it by hitting Command S on my MacBook, and now I'm going to erase the old contract, deploy this one, and mint token 5 and get the URL for token 5, and there it is. https.com example.com images/5.jpg. Make that a little nicer. Okay, cool. So this is how we can have JPEGs associated with our smart contract, which is on the blockchain. Hopefully, when you looked at this, you noticed that, hey, wait a second, this doesn't make sense. If we only allow message.sender to initiate the transactions, then if we buy something on OpenSea, how on earth is this going to work? Because if I try to buy this, I'm not the owner of this particular NFT. So when I hit checkout, I'm not going to be able to move the NFT out of this person's wallet into my wallet. Or I guess it's technically not inside of the wallet, but I don't have the authority to change this associative array over here, changing that particular NFT to my address. That's what happens when the ownership changes. So how can we solve this? Well, according to the ERC721 specification, we can have a function called setApprovalForAll, which is going to enable or disable approval for a third party, an operator, to manage all of message.sender's assets. So what that means on OpenSea is you can allow OpenSea to manage all of your assets, or at least all of your assets for a particular NFT collection, and that will allow them to move the NFT out of your wallet and into the buyer's wallet. So we can actually see that in action here. So this person must have granted OpenSea access to, let's copy this. It must have granted OpenSea approval to move the asset out. So if we look at Etherscan token approval, you can actually see that in action. So I'm going to put this person's address in there. And if we look at ERC721, okay, here he has approved this Doodles asset to be controlled by OpenSea. Okay, now this particular approval thing is coming from this being set. All right. Now you can imagine that this is kind of dangerous because if you allow another address to move around assets for you, then it can steal them. And this is certainly a somewhat controversial design decision for tokens because it certainly introduces a security vulnerability and there have been token thefts because of this kind of a thing. But this is the specification and that's what we have to learn about. So let's keep going with this. Now let's create a data structure that allows us to track this thing. So what it's saying is we need to be able to approve or disapprove. So what we are going to have is a mapping from address to another mapping that goes from address to Boolean, and we're going to call this operators. Okay, what on earth is going on here? Well, this is going to be message.sender. This is going to be the address you are approving, which the example we've been using is OpenSea smart contract, and then a Boolean to say if it's approved or not. And now we can set this. Well, I need to copy over this function, don't I? So let's copy this over here, and then we're going to take this variable and say message.sender will be the first address. The operator is the one we are granting privileges to, and we will say that they are approved or not. Now, how can we actually set this inside of the transfer? Well, what we need to do is say only the owner is allowed to transfer things, but the other thing we want to check for is if message.sender is approved for the from address. So what we will do is operators from, and then message.sender, and this just will return a Boolean. So if this is true, then this will pass. Okay, so what's going on here is saying message.sender can obviously move their own assets, or if message.sender is an approved operator for where the NFT is coming from, then we are allowed to conduct this also. Now, there is something that we need to take care of here. After this NFT has been transferred, then we should set this thing back to false. So because the asset is no longer owned by this person anymore, so we should just get rid of the privileges so there's no floating privileges. So I'm going to do operators and get from and .message.sender, and then we're going to set it back to false. Okay, what just happened? Oh, I put the variables in wrong. Sorry. So this is from, and this is from also. Let's see this in action. We are going to deploy this contract, and we want to set an approval. So right now I'm operating as 5B3 as usual. I'm going to mint it, and now I want to approve this address to be able to manage all of my tokens. I'm going to copy this, put that in here, and this DD87 address can now manage all of my tokens that are owned by 5B3. Okay, so we're going to set this to true and transact. Now that that is set, then we can see the operator moving the token on behalf of the original owner. So let's copy the original owner and from, and let's say we're going to move it to this address, AB8. We'll copy that, put it in here, and we will move token 5. Now, the person who can actually conduct this transaction is either the owner or the approved one. Let's do the approved one just to make this interesting. And before we do that, let's see that the owner of token 5 is in fact 5B38. We conduct the transfer, it goes through, and when we check the owner again, it has moved to AB8. Okay, now it probably would be really handy to know if an address is approved for another address. So the ERC721 specification has this is approved for all function over here, which is just returning the values that are inside of here because it returns bool, as you can see. So we will just return this, except message.sender is owner, obviously. Okay, so setApprovalForAll and isApproveForAll lets you manage any NFT regardless. If you wanted to give someone more granular privileges, then you could use approve, and that will only allow it for a certain token ID. So this is safer if you wanted, say, a smart contract to be moving only particular token IDs. There's just no reason to do setApprovalForAll because that gives you too much privileges. So we're not actually going to implement this one for now because I don't want to bore you with the details, and we're going to move over to OpenZeppelin fairly soon. But I just wanted to show you how ERC721 gives you a mechanism to move assets that are not owned by you to another address, assuming that the original owner has given the privileges to the appropriate smart contract or wallet. Now, there is one more interesting thing that we need to cover that you may have been wondering about. You will note that OpenSea seems to pick up pretty well that, this is token ID 8066, 2331, 1633, and so on. So how does OpenSea know all of these numbers in the first place if our contract, well, we said it could go from 0 to 99, but OpenSea is not going to read the source code inside of our smart contract and determine that, because this is pretty arbitrarily structured, right? In fact, the ERC721 specification specifically says, while some ERC721 smart contracts may find it convenient to start with ID 0 and increment by 1 for each new NFT, callers shall not assume that the ID numbers have any specific pattern to them and must treat the ID as a black box. Okay, so how can OpenSea know this? Because there's no guarantee that the IDs will be sequential. Well, that is where the events come in handy. So whenever you conduct a transfer, you are supposed to log that event to the Ethereum blockchain, or log or emit an event. That means the same thing in the context of Ethereum. So when you look at the actual smart contract for this, let's again go back to contract address. If we look at the events, then we are going to see a transfer from a certain address to another address and another topic, which is the token ID. So there was a transfer from this address to this address using this token ID, which is written in hexadecimal. But if we convert this to hexadecimal, we'll see it corresponds to the token ID. By looking at all of the transfers, that's how you are able to figure out, well, which token IDs exist, and two, who owns them. Because remember, if you look back here, we can, once we know all of the token IDs that exist, then we can, outside of the blockchain, just keep calling owner of over and over again and find out which addresses own things. That's how OpenSea is able to know who owns each of these assets. Okay, so if we wanted to actually implement this ourselves properly, we can create the event like so, and then emit this event. So we can, on a transfer, emit transfer, and this is going to be from to. Okay, another thing that we need to do is when we mint this thing, this is also considered a transfer, because if we mint something but we don't emit an event, then OpenSea or other marketplaces have no way of knowing that token came into existence, or at least not it's very inconvenient for them to find out. So we will also emit a transfer event here, and this will be from address 0. It will go to message.sender, and the token ID will be the token ID that was just created. Similarly, we have events for approval and approve for all. So based off of the thing we did in the last video, if we wanted to follow the specification, we also need to specify an approval for all event and put that, inside of this function. So emit, approve for all, and the owner will of course be message.sender, and the operator will just be the operator. So I will delete this, and approved is if the approval was given or not. Okay, at this point, we've covered almost everything. So we've discussed what these events are. The only thing we haven't looked at is balanceOf, which we will get to the next video. The last thing that we're going to look at is the balanceOf function. Now, this is rarely used in practice, so I'm not going to go into it in too much detail, but it is helpful to know what it is and what it does. What it does is it counts all NFTs assigned to an owner. And this means if you own token ID 5, 10, and 12, then your balanceOf would be 3. If you ask it about the 0 address, it's considered invalid and it should throw an exception. Okay, let's implement it. Now, how this will traditionally track things is with a mapping that goes from address to UNT256, and this would be stored in balances. When we mint it, we're going to want to increment the balance for this address. So when it's minted, now they own one piece, or at least one more piece than they used to, so the balance is incremented. The other time that someone's balance might change is on the transfer from. So the person who is sending the NFT has their balance decremented, and the person receiving the NFT has their balance incremented. No surprises there. And so the actual implementation will simply check that we're not asking about the 0 address, and then just return the balances of the address in question. So let's see this in action. We will deploy our contract as usual, and the address we are using is 0A0. So let's copy that and mint a few NFTs for ourselves. We will mint 5, 12, and 10. Our balanceOf, as expected, should be 3. And if we conduct a transfer, then this should go down. So if we transfer from our own address to a different address, and let's transfer number 5, we can oops, I didn't switch there we go. Let's do number 5, and we see that our balance of has gone down. And if we look at the recipient, we expect to see a balance of 1. If we ask for the balance of an address that doesn't have anything, then we will get 0, which is to be expected. We are now ready to dive into the OpenZeppelin contract and understand what's really going on. When we first look at the ERC721 NFT implementation by OpenZeppelin, there's going to be a lot of unfamiliar stuff at first glance. That's why I wanted to really build out the protocol step by step so that you don't get overwhelmed by seeing a bunch of new stuff here. With the exception of the strings library, which we use to convert integers to strings, a lot of this will be unfamiliar, but that's okay, we're going to cover it later. There are 2 new things that we see here. One is a string private name and a string private symbol. These are later paired with getter functions, name and symbol, and these 2 are part of the extended metadata option for ERC721. And if you look at a NFT contract, you will see them being used by Etherscan and by other websites. So Bored Ape Yacht Club is what was set for the name, and BAYC was the token. In fact, if we were to call those functions over here, let's find name, and we see it is Bored Ape Yacht Club, and token, or I'm sorry, and symbol would be BAYC. This is optional, but you should definitely include them in your contracts. But don't worry, because OpenZeppelin will include that for you. So let's keep going. Over here, we see the mappings that we had created from earlier. We had just looked at the balances, which is keeping the per address balance of how many tokens somebody owns inside of a collection. We saw the owners, which is the mapping from the token ID to who owns it. And we have the operator approvals, which is saying for this particular owner, has he or she provided operator approval to an external address, true or false. Remember how we said the single token approval is more secure because it doesn't offer as many privileges? Well, here we have it. For a given token, who is authorized to use it besides the owner? In the constructor phase, the name and the symbol are set, but that's all. Supports interface is not something we've seen before, but we'll cover it later. Here is balanceOf, which is the function we worked on earlier. As noted, the 0 address cannot have a balance. Otherwise, it just returns the value that's stored inside of the mapping. OwnerOf is the same function we implemented at the beginning. It just returns who owns a particular token ID. And of course, the 0 address cannot own a token ID. We just looked at name and symbol. These are the functions that return these private variables. TokenURI, this is something we had implemented earlier, which gave us the off-chain URL that to point to the actual asset, which were JPEGs in our case. Base URI, you'll see something interesting here because it's hard-coded to be an empty string. But what they actually expect you to do is to override this internal function with the actual base URL. And when you override it, then that's going to do what we did earlier. It's going to take the base URI, which comes from this function, which you should override, and then effectively concatenate it with the token ID, which is converted to a string. So this is how you can have a per token ID URL. You'll note that this doesn't really allow you to have an extension at the end. So if you wanted to have a .json or a .jpeg file, you'll have to override the entire function yourself. Approve is a single token approval. So this one allows an owner of a particular token ID to give authority to an external address for that particular token ID. One thing that can help make sense of the pattern of code in this library is that the actual implementation is carried out by internal functions that are prepended with an underscore. So if we look for the implementation of approve, then this is where the token approval is actually assigned the address that is approved to manage it, and the event is emitted. So this is the actual business logic, but it's internal, and external contracts or wallets cannot just call it because it needs to be gated with the require statements that make sure that only the people with the authority to conduct this operation are conducting it. So first of all, we have the checks, and then we actually carry out the business logic. The internal function actually conducts the logic, and the public gives you access, but between it, there are some security checks in place. And you will see this pattern a lot, where you see a function with the external facing name being public, but the internal one being prepended with an underscore and being inside of the public facing function. GetApproved simply returns the address that is approved for a particular token ID. SetApprovalForAll is the same function we had implemented earlier in order to allow marketplaces to trade tokens on the seller's behalf. So setApprovalForAll is actually implemented in this internal function over here. And it's just setting the nested mapping the way we did earlier and emitting the event that is required by the specification. IsApprovedForAll returns what's inside of the mapping, and transferFum implements the transfer function that we had done. But before it does that, it checks if the person is approved or owner. So are they the owner of the token, or have they been added as an approved operator by the address? Now note this funny message.sender over here. This doesn't quite look like what we were expecting it to. Again, this is one reason that I wanted to actually implement it ourselves so that we don't get overwhelmed with all of these implementation details, but don't worry, I will get to that later. Remember how SafeTransferFrom had two possible signatures? One had bytes and the other one didn't. Well, under the hood, OpenZeppelin is just going, if you call the SafeTransferFrom signature without the bytes as part of the argument, then it's just going to call its own SafeTransferFrom implementation with the bytes being empty. And here is the SafeTransferFrom with giving bytes as an option to be specified inside of the argument. SafeTransfer conducts a transfer and then checks if the receiver is, if they are a smart contract, are they actually able to receive the tokens? Now, this might look kind of funny, but Ethereum transactions are all or nothing. So if you conduct a transfer and then revert it, then the transfer is reverted also. Exists is just a nice shortcut function for us checking. Remember, we can't get a URI for a token that is not part of the collection. Well, this is a more general form of it. Just if the mapping holding the owners is not pointing to the zero address, then it's assumed to exist. Is approved or owner is what it sounds like. It just checks for a particular token ID. Is the spender allowed to spend it, or are they the original owner via this mechanism? Mint and SafeMint is analogous to transfer and safe transfer. What SafeMint is going to do is do a regular mint and then check if the recipient was a smart contract. And if so, then make sure that it actually has the mechanism to interact with ERC721 contracts. This is something that I'll get into more detail later, so don't worry about that for now. Here's the actual mint functionality. First of all, we require that we can't mint to the zero address. And second of all, we can't mint something that we haven't minted already. And here's the changes in balances that we had talked about. And this is where the ownership is actually set, and it emits the event that is required. The before token transfer and after token transfer are utilities that you can specify on your own later. So what it does is it gives you an ability to override this function and say, oh, maybe I don't want to transfer to certain addresses. So inside of this function, I could just replace it with a list of addresses that I don't want to transfer to, or have some other logic, maybe like a time lock or something. And here's the check on ERC721 received. Again, this is something that we will get to later, but this is for dealing with sending ERC721 tokens to smart contracts. Okay, and then that covers it. There was, even after all of the material we've looked at so far, there was still a lot of stuff I said I have to cover later. That's why I wanted to break it down piece by piece. But the stuff that we'll be covering later is not as core to the functionality to ERC721. So we will not need to review that in depth until we've actually implemented some tokens using this library. And then we'll be able to have more motivated examples for studying these new functions. Now that we've covered the groundwork for the OpenZeppelin ERC721 implementation, we can start moving pretty quickly in implementing our own NFTs using that library. So I've imported the OpenZeppelin ERC721 solidity file that we just looked at, and I've created a contract that extends it. Now, the compiler is unhappy with me right now because I haven't overridden the constructor. And remember, the constructor in the source code that we just looked at requires us to specify a name and a symbol. So let's do that. We will have our own constructor, which won't do anything yet, but then we have to override the constructor for the parent contract. So the first argument is the name, and the next one is the symbol. So let's call this my NFT. And MN. Okay, that's a pretty pathetic name. I'm sorry, but it gets the point across. So we will close it off like this, and I will recompile it, and now it's happy. Okay, so let's actually run it the way it is right now to see what's going on. Okay, so I've compiled it, and I will select the file that we've been using. Okay. Now we've hard coded what the name and symbol are, so it's my NFT and MN. The base URI, well, we cannot ask about token URIs right now because nothing has been minted, and we don't actually have the ability to mint anything. But here we have our transfer functions created for us, as well as the approval functions and the balance of, which of course is going to be 0 for everybody because nothing has been minted yet. So we will add the mint functionality in the next video. Okay, let's add the mint functionality. We are going to create a function called mint, and what we are going to have to do is call the internal mint function. So because we've inherited from ERC721, this function, mint, is available to us. It's internal, and we are creating a child contract, and internal functions are available to the children. This is kind of like protected in Java, if you have done that before. So let's call the internal mint. What is required as part of the signature there is a to address and a token ID. So we will just say it will be minted to the person who's calling it, and then we need to specify the token ID. So well, let's follow convention and do it this way. So how are we going to set this? Because obviously if I try to compile this, it's going to yell at me. Well, it's going to yell at me about a couple things. One is I didn't specify function visibility here, so let's get rid of that. And I also didn't specify token ID. So the pretty classic way of handling this is to specify the token supply manually. Now, some variations of ERC721 have token supply built into the specifications. We will get that later. We will get to that later, but for now, let's just do it this way. uint 256 public token supply is equal to 0. You don't actually need to do this because variables default to 0, but I'm just doing that to make it explicit for now. So when you're starting off, nothing has been minted. So when this is minted, then the first NFT will be token 0. And then after that, we are going to want to increment the token supply like this. So every time somebody calls mint, the sequential ID will be minted. So let's try that out. Let me get rid of this old contract and deploy this. When you deploy this, make sure that you select the file you're actually using, because if you select OpenZeppelin's implementation, then the mint function won't be there because they have _mint, which is not public, and you can't see it. All right, let's mint some stuff. So if I hit mint, okay, supposedly I just created an NFT. Let's see if I actually did. So who is the owner of token ID 0? Well, that's me. Okay, fantastic. Now let's see my balance, and I have 1. All right, so if I mint again, then my balance should be 2. And if somebody else mints, I will just change to this account and press mint. Now the owner of token 2 is that new address. Okay, cool. Now this is how tokens come into existence. So let's make this a little bit more sophisticated, because two things are missing here. One is we want to generally limit the supply of NFTs. So I assume most of you watching this are trying to build NFTs for like a profile picture collection, and those typically are limited to a supply of like 1,000 or 3,000 or 5,000 or 10,000 or something like that. So we want to limit the supply, and that's probably pretty easy to do. And the other one is we want to accept payments. So I will show you how to do both of those in the following videos. Okay, limiting the supply should be quite easy. Usually the pattern is to specify the maximum supply up here with a constant. And let's just say that we're setting the maximum supply to 5 just so that we can easily test. This would be quite small. You would probably make it more like 5,000, but let's say 5 for now. And the other thing we'll want to do is to make this constant because, well, first of all, your customers generally expect that this should not be modified. And second of all, constant variables are actually more gas efficient than regular variables, because when you have a public variable that isn't a constant, this gets stored inside of the Ethereum state, and you have to do read and write IO access to access this particular variable, and that can drive up the gas costs. We'll talk a little bit more about that later, but if you really want to dive into it, you can take my gas course on Solidity, link in the description. Constant variables are cheaper because this is actually stored inside of the contract's bytecode. So as the code is executing, it can more directly access that variable. Anyway, what we would add over here is a require statement, and we want to say token supply is less than max supply, and we would say supply used up or something like that. So will this work? Well, if we are currently at token supply 0, this will pass. At 1, it will pass. At 2, it will pass. At 3, it will pass. At 4, it will pass. But at 4, this will get incremented to 5. And 5 is not going to work because 5 is not less than 5. So we will have 0, 1, 2, 3, and 4, which is the total supply of 5, as expected. Okay, now let's discuss withdrawing the funds from the contract. The way this is traditionally done is by making the contract owned by the person who deployed the address and then only withdrawing to that address. So there is an OpenZeppelin library called Ownable.solidity. And what this does is it keeps track of the address that deployed the contract so that this address is able to have special privileges with the only owner modifier. So check owner is, of course, going to check if the owner, that private variable, is the same as the person interacting with the contract. So what this would look like is this. It's going to extend the ownable. Well, we need to import it first. We would import OpenZeppelin contracts. What is it? Access ownable.sol. Okay, that compiles. Good. And what that's going to give us access to is the modifier only owner. So this is what the withdraw function would look like. Okay, so what is going on here? Well, when someone calls withdraw, then the person who calls withdraw will get sent the money, but only the owner is able to receive the balance, and the entire contract balance will be sent to them. So this is a very common pattern that you will see in NFT implementations. So I wanted to show it to you. There are some things I don't like about it, which I will explain in a second. But first of all, let's see it in action and see that it actually works. So we're going to deploy this contract. And for the sake of convenience, I've changed the price to be 1 Ethereum. So that way I don't have to keep copying in all of those numbers with a bunch of zeros in them. So first of all, let us have this address deploy the contract. And when we look at the owner variable, the owner function, then we're going to see it 03C6F. Okay, now let's have another address mint an NFT. They will have to pay 1 Ether for it, and they will mint. Let's have them mint 2 NFTs so we can have 2 Ether inside of the contract. Okay, they minted 2 NFTs. Now, if this address that is minting tries to call the withdraw function, then it's going to get blocked because it says ownable caller is not the owner. Okay, the security is working as expected. So if we go back to the original address that deployed the contract and then hit withdraw, then it doesn't block it, it worked. And if we look at the balance of this address, now it has 102 Ether or 101.99999. Well, that's because the other address put 2 Ether into the contract and this one withdrew it. Okay, so what don't I like about this? Well, it gives you some additional functionality that lets you shoot yourself in the foot. The first one is renounce ownership. So if you do renounce ownership, what it's going to do is transfer ownership to the 0 address, which means any function that has this only owner modifier in front of it is not going to work. And if you renounce ownership before removing the balance, then the Ethereum would remain stuck in this contract and you would never be able to withdraw it. This has actually happened to a couple projects sometimes, so I think it just creates an unnecessary risk. The other one is to transfer the ownership. So you could transfer the ownership to another owner, and this just creates an avenue for something to go wrong. So if you know that, because if you end up transferring it to an address that you don't control, then you end up in the same situation where there's a bunch of functions that you can't use anymore. Now, depending on your design pattern, this isn't necessarily a bad thing. Some people might expect you to renounce ownership so that they know that the contract is more decentralized after a certain point. And that's fine. But this is something that you should think about the pros and cons of using before you actually do it. If you still want to use this Ownable library and this pattern, then what you can do is override those functions. So you could say function renounce, let's copy it, renounce ownership. So we're going to copy this and replace this with an override, and we don't need this modifier anymore. And we will just replace this with something that will just block it. So it will require false, which is always not going to work. And we could do the same thing for transfer ownership. And then replace this with an override, and we don't need this. So if we deploy this contract, so I'm going to erase the old one and deploy this. If you accidentally hit renounce ownership, then it gets blocked. But now you're adding these safeguards in that you created a lot of complication for yourself because you were using this library. So I'm not the biggest fan of this thing. If you lose track of ownership, you might lose some functionality, and that also doesn't allow you to update the royalties anymore or any other data on OpenSea because OpenSea doesn't see you as the owner of the contract, so you lose some privileges. I personally think it's better to do something like this. Address deployer is, and then set the deployer here is equal to message.sender. And then maybe make this immutable. So what a mutable variable does is it can be set during the initialization, but after that it can't be changed. And then inside of withdraw, I would require, or actually what I would do is just hard code this to the deployer and then transfer the balance, and we don't even need this check anymore. So if somebody else calls withdraw, it doesn't matter because it's going to go to our address. Now, I guess if you're careful, this isn't really an issue, but I don't think it's a good idea to code in things that can go wrong because Murphy's Law might eventually sting you. But this is the conventional way of doing it. You're going to see this pattern a lot. Just be aware of the drawbacks. In this video, I'm going to explain what IPFS is and why it is so popular with NFTs. I'm not going to be explaining in detail how it works. That's been well documented online, so you can look it up on your own. But I want to get you to know enough about IPFS so that you are able to start using it and you know what issues to look out for. Okay, so NFT assets need to be stored off-chain usably. There's some exceptions to this, but most of the time the assets that are associated with an NFT, like a image or a video or a piece of music, is too big to be kept on chain. And if we work out the calculations, which we're not going to do here, in general, you can think that 1 kilobyte of data requires about 0.014 Ether to store it on the blockchain. It actually would take more than that, but this is the minimum amount. Now, you may note that the price of gas changes with time. So this is making an assumption that Ethereum cost 20 Gwei at the time. If you go to a website like etherscan.io/gas tracker, it will tell you what the current gas price of Ether is. Let's actually do that really quickly. So etherscan.io/gas tracker. Okay, it's actually worth 13 Gwei at this time. But historically, it's fluctuated between something like 10 to sometimes over 100. So it can vary a lot. But either way, 0.014 Ether is quite a bit of money. And that's just for 1 kilobyte. Most pictures are not that small. 100 kilobytes is pretty normal. So you're already looking at 1.4 Ether to store an image. And of course, that's quite expensive. So a solution to this is to point to a URL off-chain. And some NFTs do this. But there is a drawback to this. One is the blockchain itself is immutable, and you can't lose all of your tokens all of a sudden. But that doesn't apply to HTTP protocols because images there could disappear. For example, the person who launched the NFT might stop paying for the DNS, the artist stops paying for the web hosting, or the web hosting itself has an issue or goes out of business, or the content becomes censored, depending on country or locale or whatever. So this doesn't make for a good customer experience if, okay, you have the NFT associated with your address, but the asset isn't there anymore. So this is a fundamental problem with addressing content with the DNS or IP addresses. They simply do not have longevity, and they are quite mutable. And of course, we know NFTs cost a lot, so this is actually quite a problem because buyers don't feel good about paying thousands of dollars for an NFT, knowing that it could vanish just because something happened to the web host or the artist stops paying, or even in funnier situations, the artist intentionally changes the asset that is stored on the website. Okay, so one way to get us in the right direction is to think about hashing. So if we store the hash of the image, then now the association between the actual token ID and the asset that it's representing isn't changeable anymore. So this would solve the situation that, okay, there's no ambiguity about what picture is associated with this particular token ID. But the problem with that is that hashing doesn't work for actually displaying the content. It just works for ensuring that the content wasn't tampered with. So a hash will prevent tampering, but it doesn't help with addressing the content because you can't reverse engineer a hash. But that actually gets us to what the final solution ends up being. If you could use the hash itself as a form of an internet address, then anybody who is able to produce the content that resolves to that hash is able to host the image. And this is actually how IPFS works, where the hash of the content is itself the address. And I'm kind of oversimplifying some things here, but that's basically how you can think about it. Again, if you are interested in the exact details, you can look around. This has been pretty well documented multiple times. When it comes to IPFS, the network will try to route you to different nodes inside of a peer-to-peer network that hold copies of your file. So you can think of IPFS as being pretty similar to BitTorrent. In BitTorrent, you have an address, but what it's really doing is giving you a mechanism to reassemble the file from multiple different places. So if you take this image over here and took its IPFS hash, this is what you would get. And this is how you would actually try to locate the nodes inside of the IPFS network that is holding a copy of this image. IPFS also supports a notion of folders, so you can have a base folder and then different files inside of it. Now, I just named them 0, 1, and 2 like we would with an NFT, but this could be dog.jpg and cat.png or 2.json. But keep in mind that because these are hashes, if you change anything inside of the folder or anything with an image, then the hash changes. And that's a good thing for us because we want to make sure that the content is not tampered with. But it also means that you need to get it right. The primary advantage is because there's no single owner over the content, then even if the artist stops paying for hosting the image behind the IPFS, I'll get to that in a second, someone else is able to host the content themselves, and they don't have to worry about not owning the URL. Because as long as they can produce the hash, then it's able to be located on the network and the NFT image is able to be shown. So if the smart contract is hard-coded to a certain IPFS address, then you can be sure that the image will never change, just by the nature of how the hashes work. Here are some important things that you need to know. IPFS does not store the files. It just handles the content addressing. So you still have to host the file yourself. Unlike BitTorrent, there isn't really an expectation that people are going to be hosting copies of the file. So you either have to host it yourself or pay for it. And this could be done by running an IPFS node yourself, or using some third parties, which I'll talk about later. So what are some drawbacks of IPFS? Well, if nobody is hosting the content, then nobody will be able to pull up the image. More importantly, if you have a folder full of assets and you lose that folder and nobody is able to reproduce the IPFS hash again, then it won't be possible to display the image. IPFS is very slow. It's a peer-to-peer routing where it's bouncing around different nodes trying to find who has a content. So resolving an IPFS request can sometimes take up to a minute in my experience. So because of this, IPFS is not needed for most applications. But for NFT, where there isn't expected to be longevity in the images, this is not a problem. It's actually a good thing. Nowadays, buyers are going to ask questions if you don't host the images on IPFS. It's kind of become standard at this point for most NFT projects. So you should use it. Otherwise, you're going to expect NFT collectors asking you questions. But I can't assume that you're only going to be using NFTs for the ways that they have been traditionally used as profile picture collections. If you have a situation where you specifically want the data to be mutable and it's not a problem that you have centralized control over the images, then it's totally okay to use HTTP. There's no law about it or anything. I'm just trying to inform you of what the market norms are at this time. So actually hosting it, as I alluded to, you can run an IPFS node yourself and pin your own content, or you can use a centralized provider like pinata.cloud. This is a provider I've used and I found them to be pretty user-friendly. Or you can use a decentralized provider like aleph.im. So this is itself a decentralized protocol that has its own token, and computers in the network offer some of their computing power and bandwidth in exchange for being able to earn more tokens. So this behaves somewhat like a decentralized Amazon Web Service. And to use the network, I'm going to show you how to do this later. You just need to hold aleph.im tokens in your wallet, and that allows you a certain amount of storage and bandwidth on the network. That's all for this. I'm going to give you some demonstrations on how to use IPFS next, but this should give you a pretty good idea of what IPFS is, why we use it, and what to look out for. To get yourself set up, I first of all recommend that you download the Brave browser from brave.com, because this browser lets you conveniently view IPFS files. So that's what I'm going to be using for this video. This is a derivative of Firefox, so it will work with the same extensions. Now, the images need to be prepared first, because remember how we saw the NFT pointed to a JSON file, which then pointed to the images? Well, until we upload the images, we don't know what the IPFS hash of those images are going to be. So we won't be able to create the JSON file for the NFT. So I've created a couple images that I'm going to use for the NFT data. Here they are. Some of them may look familiar, with the exception that I've added sunglasses to them. So this entire folder needs to be uploaded to IPFS. One thing you need to be really careful of if you are using a MacBook is that sometimes you're going to have a hidden file in here called .dsstore. So make sure you look for any hidden files on a Mac, because if there's any hidden files in here, it's going to change the hash of the folder, because obviously the file content is different. So be very careful with that. Now I'm going to show you. So the first thing that I'm going to do is upload this to Pinata. So Pinata is a service for hosting your files and making them retrievable from the IPFS hash. Because remember, an IPFS hash is related to content, but nobody on this decentralized network is required to host the file. They just route you to where your files might be hosted. And you can use this service to actually host your files. So I've already uploaded them over here so you can see the hash that is created, but I'll just remove this so that you can see this process all over again. So just to go to from the beginning, if you go to pinata.cloud and then hit login, it will take you to your dashboard where you can upload your files. So you will hit upload, folder, select, and I already have the path to my images here. So I'm going to hit upload, and let's call this NFT course images. And after a while, it will show up. There it is. So to actually view this, you can copy this link. And if you open another tab, you can go to IPFS:// and then the IPFS path, and then the item inside of the folder. So you can do, let's say, 0.jpg. As I mentioned in an earlier video, IPFS is slow, so this may take a while to resolve. And there's the first one. Let's try another one. Let's try 1.jpg. I didn't put the IPFS. Now you want to be really sure that you're going to be able to reproduce this hash, because that's what gives your NFT images some permanence. So another way to double check it is to download the IPFS desktop client. You can just Google search for IPFS.io desktop client and you'll get to this page. I've put the link in the description too. So what that will do is it will give you this dashboard after you set it up, and you can upload it over here. And you want to check that the hash being created here is the same that you're getting over here. So this is QMF8WG, QMF8WG. And this makes sure that the .ds store file hasn't popped in after Mac puts it in there or whatever else is going on, because you want to be completely sure that this is reproducible. The final way to store NFT files is with aleph.im, which is a decentralized hosting service. So in order to use this, you're going to need to have some aleph.im tokens in your wallet, and that will give you a quota of how much you are able to upload. So you can get there by going to aleph.im and clicking use cases and scrolling down until you get to this section over here, pin your files, folders, and so on. Then you would hit upload, and then you're going to have to set it up by connecting your account, and this is the one that you want to use. Connect wallet, public upload, and I would pick a folder to put in here. You need to keep these tokens in your wallet. Now, the nice thing about how it's configured right now is you don't have to actually spend it, but you do have to hold it and not move it out of the wallet, otherwise the nodes might not store your images anymore. Okay, so that was all pretty simple. Now that we have our hash here, we're ready to create the metadata. A mistake that I see happen a lot is not handling the IPFS URL properly. Let me give an example. So let's go back looking at an image from earlier. And if I were to say IPFS://this/1.jpg, then okay, it gives me this. That's fantastic. But oftentimes the browser will reformat this to take you to an HTTP gateway. Now, what's the problem with this? Well, this, if we have a link to an HTTP gateway, then we're relying on this DNS being valid, which is not a good assumption to make, because then that defeats the purpose of using IPFS. So it's very important that for your image, you have an IPFS protocol followed by the actual IPFS. And you do not want an HTTPS link in there or something that has a traditional domain name. And of course, do not forget this IPFS prefix. Now that we've uploaded the images, we are ready to create the metadata file. So just by way of reminder, the TokenURI doesn't point directly to the image. It will point to a JSON file, which will then point to the image. Let's do that. So OpenSea describes what this metadata file or JSON file should look like, and we can just follow it. Now, you don't actually need all of these attributes if you don't want to have them. At the bare minimum, you just need the image, and this will point you to where the image is. In this Bored Ape example, you can actually see that they've only included the image and the attributes key, and the rest have been removed. So if you don't include the name, then OpenSea will just call your NFT number whichever index it is inside of the collection. Otherwise, you could put the name over here. This description will be associated with this description field over here, but of course there's no description, so that is empty. And here are other items that you can include. At the very least, you should have the image. And the image, of course, is going to be an IPFS hash, just like it is here. And that's why we needed to put the images up first, because we don't know in advance what the image IPFS hash would be. So let's see what that would look like. So I have already created the JSON files for what we've just did. This link over here was one of the images that we had created from earlier, and we can just look at each of these files over here and see that they work as expected. Okay, you get the point. Now, what I'm going to do next actually is remove the .json extension, because this just seems to be the convention with the NFT metadata files, and it also is more convenient for creating the smart contract. Now, that's not necessary, but it just seems to be the norm. Go to the metadata and just mv0.json to 0, mv1.json to 1, mv2.json to 2, mv3.json to 3, and mv4.json to 4. Now, of course, when you have thousands of images, you need to do this automatically, but that's not a detail I want to get involved with right now. One other thing I would recommend just to make things nice is make sure that you format the JSON. I'm not sure why Sublime didn't store this way, so if I just do python.m json.tool 0, then it's going to correct the formatting for everything. So you can just do that with all of the files. The next thing to do after you've made all of these changes is to upload this file to IPFS. So we are going to do that right now, like this. I already have a file named metadata in here, so I'm just going to rename this to be NFT course metadata and put it in here. NFT course metadata. Again, make sure that there is no .ds file in here because Mac likes to put that in. Okay, it's been uploaded. So let's see what it looks like. We will copy, we can click in here to see the directory, and here is 0, 1, 2, 3, and 4. So let's look at 1. And here it's pointing us to our other image, and we can validate that over here, and sure, there it is. Okay, so dealing with IPFS can be the most annoying part because there's a lot of moving parts. You definitely have to automate it if you're dealing with a lot of images, but this is good enough to get us back on track for finishing up our NFT. All right, congratulations. We are now ready to create a fully functional NFT. Now that we have all of our images uploaded to IPFS, we are ready to override the base URI function, which will then make TokenURI point to the correct location. Because we have all of our metadata files being called 0, 1, 2, 3, 4 without any extension, then the way this function works right now will just work because it's going to replace our IPFS URL with the particular metadata index that we are interested in. So let's override this. We do, and we're going to put in our IPFS URL. So this is the IPFS URL we've been using. We will say IPFS : this, and then we need to put a slash at the end so that this will be formatted properly. Okay, oops, I forgot to say override. And, well, it's saying that this can be restricted to pure, which, okay, that's fine. We can do that because this is just returning a hard-coded string. It's not returning any thing that it reads from the blockchain. Okay, let's deploy this contract. And if we call TokenURI right now, then it's not going to work because we haven't minted anything. And remember, the actual implementation is going to check that, oh, this needs to been minted before. So require minted, if we look for that, if we look for require minted, it's going to check that the token ID actually has been created. So we will need to mint it first. So we will pay 1 Ether to do that. We will press mint, and then we will get the token URI of token 0. And there it is. So let's see where this takes us. Again, we will use the Brave browser because it just works with IPFS. We plug it in, and there is our metadata. So this should hopefully take us to the picture. And when we put this in there, there we go. So it's someone with regular sunglasses. Okay, so we now have a fully functioning NFT. Now, there are still some more features that we need to add to this so that it will behave the way that we normally expect NFT workflows to work. But this can be put into OpenSea right now, and everything will work as expected. Now we are ready to deploy this NFT to OpenSea, but there are several things we're going to have to take care of first. One is if we try to deploy it as it is right now to the Ethereum mainnet. I got to this by hitting this drop down over here, which is normally JavaScript London, and then hitting injected web3. Okay, so this address over here is the address that I have in the MetaMask. I don't know if you guys can see that, but it's the same as over here. If I hit deploy, then it's going to ask me for confirmation, which is fine, but the cost is going to be $135, which is pretty expensive. At the time I'm recording this video, Ethereum is lower than what it has been recently, so it could actually cost quite a bit more than this in a typical case. So we don't really want to test our NFT on the regular Ethereum network. Obviously, when we deploy it to our users, yes, we have to pay that fee. But when we are just testing, but for the sake of testing, we don't actually want to spend that kind of money. One quick thing you can do to alleviate that is to turn on the optimizer. So you go back to one thing you can do to at least help alleviate the cost is to go back to the Solidity compiler page, hit the drop-down under Advanced Configuration, and turn on Enable Optimization. By default, the optimizer is set to 200. Now, I can't really get into the trade-off of the optimizer here because I don't want to go on a huge tangent. Again, you can look at my gas course on Udemy to learn more about that. But if you at least turn on the optimizer to 200 and then try to deploy the contract again, you will note that the estimated cost goes down to $54, which is quite an improvement. What that optimizer is doing is it's trying to make your source code smaller. What I would typically recommend that you actually do when you really deploy this thing is to change it to around 10,000. Again, I can't get into all the reasons here. I don't want to get too technical in this course. That's for the other course. But the reason for that is because setting it to a lower number will save your costs on deployment, but setting it to a higher number will save your users costs when they're actually using their contract. So let's see how this changes the deployment cost. Whoops, I have to reject the old one, excuse me. So if I hit deploy on this, confirm, then I see, oh, the cost actually went down. Well, that's probably because there was a fluctuation in network prices. But ideally, you want to be setting it to 10,000 because that's going to lower your cost in terms of deployment, and it's also going to save money for the people interacting with your contract. The higher the number you put in there, then the more money the downstream users are going to save. But for most NFTs, going past 10,000 isn't going to accomplish anything. It just levels out at that point. Okay, now I guess we're still feeling cheap here and don't want to spend $43 deploying the contract. So what we are going to do is use the test network. So if you go to testnets.nets.opensea.io, then you will actually see an OpenSea on the Rinkeby test network and lets you test that your integration with OpenSea actually works. So I should quickly comment right now that Rinkeby is going to be depreciated sometime this year because Ethereum is going through the merge and Rinkeby is not going to support the merge. So what I actually do is test on OpenSea Polygon. So if I go back to the regular OpenSea and go to Explore, then and hit all NFTs and go to chains and click Polygon, then now it's just looking at NFTs that are on the Polygon network. But Polygon behaves exactly the same way as Ethereum pretty much. And Polygon is also a very cheap cryptocurrency. So if you want to test things on a chain that is going to be around, I actually recommend testing it on Polygon. But we'll discuss that later. For now, we're going to test it on Rinkeby. And to do that, what we need to do is go to faucets.chain.link. And then we need to change our MetaMask to go away from the Ethereum network, and we hit Rinkeby. If you don't see this, that means you need to click the show hide Ethereum test network. So if this show hide test network switch is not flipped, you won't see it here. So you have to hit show hide test network, turn this on, open the drop down, and there it is. So Rinkeby. Okay, great. Now you can request testnet link. Now, this is for Chainlink, which is a service for bringing information onto the blockchain from the outside world, but they're very kind to be giving us 0.1 test Ethereum also. So we don't really need any link for this example, so we will tell them I'm not a robot, and they will give us some test Ethereum on Rinkeby. I've made too many requests, but this will normally go through, and you can see that I've done this already because when I open my MetaMask, I have that 0.1 ETH. Before we proceed, one thing we'll want to do is lower the price of the cost of minting an NFT because we don't have that much Rinkeby Ether at our disposal right now. And now that that's done, we will make sure that the correct file is selected over here and hit deploy. And we will hit confirm and view on Etherscan. So this will take some time to get through, so we will just have to wait. And it has succeeded. Now this will not yet be visible to OpenSea until an NFT is actually minted. So to do that, we are going to have to we can hit mint from over here. Now, this is not actually the ideal solution, but I just want to show you the workflow. So if we hit mint, we'll first of all going to have to put in the appropriate amount of Ethereum into the value field over here. So I'm going to go to the converter and select this, paste that into there, and hit mint. And then will ask me to confirm because this is actually happening on the test network, not inside of the local environment here. And I hit confirm. We can view on Etherscan to see the progress of this transaction. Okay, it has succeeded. And Etherscan actually recognizes that this is an NFT contract. Now let's copy the contract and go to testnets.opensea.io and paste in the smart contract address. And there it is. So you have now put the collection on OpenSea. Now, why do we see a goofy name like this? Well, I'll explain that in the next video.